Hi guys, I'm going to try this one more time. This is a couple attempts on this video and it keeps not recording my sound, and so hopefully it works this time. As promised, I have another optimization problem and just a quick video for you on it. It shouldn't take more than about 10 to 15 minutes max. So the problem we have here is suppose airline policies state all baggage must be box-shaped with a sum of the length, width, and height not exceeding 64 centimeters. So we have something that looks like this. I'll move it back up in a second here. Right. And I have a box-shaped item. That's a really, really bad line. There we go. And length times width times height. And I know that length plus width plus height better be less than or equal to 64. So the length and width and height is not exceeding 64. And I want to know, what are the dimensions and volume of a square-shaped box with the greatest volume under these conditions. So I want the max volume, and I want the dimensions there. Oops. See how easy it is to erase there? Okay, so I want the maximum volume, and I want the dimensions of the maximum volume. And so it's really good to write that down so we can come back. Now, I mentioned that it's a square-shaped box, so that means that I know that my length is equal to my width. So down here, I'm going to have this. One side note that the length plus width plus height better than be greater than 0. It shouldn't be equal to 0 because then I wouldn't actually have a box. So just a note as far as what we're looking at here, kind of on the domain of this. That's what we want to think about. So if I want to rewrite this and say I'm going to go for the maximum volume, then I'm going to say I'm going to be equal to 64. So I'm going to have length plus width plus height equal to 64. And that means that I have 2w, because if I substitute in a w here for the length, plus h equals 64. Now I said I wanted to find the greatest volume, so I'm going to look at the volume of a rectangular prism, and the volume of that is length times width times height. And again, if I substitute in for my length, I'm going to have width squared times height. Now you'll notice that here I'm trying to maximize the volume, but I have two separate variables. So I want to put it all in terms of one variable if I can. And to me, the easiest one that I can use from this equation is going to be my height, because it's easy to solve for. I can do this whole problem writing my volume in terms of the width, or in terms of the height instead of the width. By solving for width, it's just going to be, to me, a little bit more work. So what I'm going to say off of here is that my height is equal to 64 minus 2w, and that's nice and easy to sub in. So I can rewrite my volume now as a function of just width and say that it's w squared times 64 minus 2w, which is also equal to 64w squared minus 2w cubed. Now I want the maximum volume. So as soon as I see the word maximum or minimum, I'm thinking of a derivative and looking for my critical points. So if I find the derivative for my volume, I have v prime of w, my derivative of volume, is equal to 128w minus 6w squared. And I can factor a 2w out of both terms, and I'll get 64 minus 3w. So if I want to find my critical points, right, because I want to find my max or min, my potential max or min points, then remember that I want my first derivative with respect to w equal to 0. So either I come out with w equal to 0, or let's see, whoopsie, 3w equals 64, and so w equals 64 thirds, which is fine. When I look at these 2 points, if I look back to the very beginning, you'll remember that I mentioned the domain, that I really want to be greater than 0, because if I have a 0 width or length or height, I have no box. So I'm going to cross out that term. I don't care about it. It's not a valid critical point for what I'm thinking about in the real world. So the only critical point I have here is this one. I have 1. Now, when you see that you have 1 critical point on the interval of interest, you should be thinking about the second derivative test, because remember, the second derivative test says that if at this critical point here, if the second derivative is less than 0, then because at that point I'm concave down, that means that I'm at a maximum. And if at this derivative I'm greater than 0, then I'm concave up, so I'm at a minimum point. So we can use that second derivative test. So let's find the second derivative of the volume. And I get 128. I'm using this first equation to do this, minus 12w. And out of that, I can factor a, well, let's see. Well, I can at least factor a, well, let's just solve. Oh, wait, we don't need to solve it. I'm not looking for inflection points. I'm off on my own world. All I'm doing here is I'm going to take my critical point from over here and find out whether my second derivative at that critical point, 64 thirds, is greater than or less than 0, because I'm just using that second derivative test. Sorry, went off on a little tangent there. So if I substitute in this, and you punch that into your calculator, I did not do this in my head, you should come up with this is equal to negative 128, which is very obviously less than 0, which means that I'm concave down, without an n, concave down. And so that means that I must be at an absolute max, because, hold on, max, because this is the only critical point that I have, is here at w equals 64 thirds, and I'm concave down there. And so it has to be the highest point in that domain that I have, okay? So I have an absolute max at w equals 64 thirds, which is great for me, okay? If you don't think about this second derivative test, you can use your number line. You can say 64 thirds is here, and you can say, okay, I'm going to test over here. The first derivative of the volume is going to be greater than 0 on this side of 64 thirds, so I'm increasing. And the first derivative of the volume is less than 0 over here, so I'm decreasing. So you know you have a maximum there. Alrighty. You're welcome to use the first derivative and look at increasing and decreasing. I think that the second derivative test is faster and it gives you the same information. All right, so what we know is we have an absolute max at w equals 64 thirds. So remember, I want to make sure I go back to my first equation. V of w was equal to 64w squared minus 2w cubed. I'm going back to that very first equation. Remember, like back here, okay, to find my maximum volume. So my max volume is going to be at V of 64 thirds. So I have 64 times 64 thirds squared minus 2 times 64 thirds cubed. And that'll come out, if you punch it into your calculator, to approximately 9,709. And your answer here is going to be in inches cubed, because you'll remember that the 64 here was in inches. Okay, so make sure you go back and check that. So that's the answer for the maximum volume. Now remember, if we look back to what we want, and this is why I always write down what I wanted the maximum volume, which I've gotten, but I also want the dimensions. So if I look at that, I can use my height equation. Remember, we had h was equal to 64 minus 2w. So I can find that as 64 minus 2 times 64 over 3, which is actually going to be equal to 64 over 3. So my dimensions, no, there's no O. Dimensions at the max volume are going to be 64 thirds, because that's my width, inches. Let's write inches by 64 thirds inches. It was a square bottom, right? So that comes from this, the width. And then my height is also 64 thirds inches. So basically I have a cube. And if you think back to when we've done area problems, let's say with the fences and stuff, and you're talking about rectangular areas, remember how every time we've maximized an area, what we've seen is that the maximum area is when we have a square. And here what you see is that your maximum volume is when we have a cube. So you're kind of seeing a trend. So my two answers here, this would be the dimensions, and this right here would be my maximum volume, and that'll take care of the problem. So I will find maybe one or two other optimization problems to shoot your way and put up on the website on Canvas. I'm also going to put up a video link to L'Hopital's rule, or L'Hopital. A lot of people don't make the H. I always put it in. I don't know why. Anyway, I don't speak French. So I'm going to put up a link to a quick video. It's 13 minutes long. It's by that organic chemistry tutor. And it's a pretty good video. It's not a long section, something that we need to cover, but I think if you guys watch that video and have a good idea of that, that is section 4.7, then on Monday we can start maybe a really quick review of L'Hopital, and then we can jump right into the antiderivatives and the integrals so that you get the taste of those before we end out the semester. And we're not, we get to where we need to be. So anyway, if you have any questions either on this or on L'Hopital or on, I suppose, anything else related to math, let me know, and I hope you have a great weekend. Thanks. Bye.